Step outside tonight, when the air is still and the world has grown quiet. Look up at the darkness above your head. The stars twinkle like scattered diamonds on black silk. But there is something else up there. Something closer than you might imagine. Between you and those distant suns, an invisible parade drifts through space. These travelers have no light of their own. They reflect only the gentle glow of our sun, too faint for your eyes to catch from Earth's surface. Yet they are there, moving in their ancient dance around our star. These are the asteroids. The forgotten children of our solar system's birth. Most people think of space as empty. A vast ocean of nothingness between planets. But this emptiness is an illusion. Space teems with rocky wanderers, each one a world unto itself. Some are as small as pebbles. Others stretch wider than cities. They tumble through the cosmic dark, carrying secrets from the very beginning of time. 4.5 billion years ago, when your Earth was still forming, not everything found its way into planets. Some material remained scattered, adrift in the space between worlds. These leftover pieces became the asteroids. They are the building blocks that never got built into something larger. The spare parts of creation itself. Tonight, as you breathe the cool night air, imagine floating among them. Picture yourself drifting beside a mountain that has no ground beneath it. No roots anchoring it to anything solid. Just rock and metal, suspended in the infinite. The asteroid belt lies between Mars and Jupiter, like a river of stone flowing around the Sun. But this river is not crowded. If you could stand on one asteroid and look around, the next one might be hundreds of thousands of miles away. Space gives each wanderer room to breathe. Yet within this scattered collection lies treasure beyond any earthly measure. These rocks carry metals that are incredibly rare on your planet. Platinum, a metal so precious that all the platinum ever mined on Earth could fit in your garage, flows through asteroid cores like silver veins in mountain stone. A single asteroid might contain more platinum than humans have ever found. Gold drifts within these space mountains in concentrations that would make ancient kings weep with envy. Rare earth elements, the materials that make your phone and computer work, exist in asteroid cores by the ton. Elements that we struggle to find on Earth float freely in the cosmic dark above your head. The asteroid called 16 Psyche may contain enough iron, nickel, and precious metals to give every person on Earth billions of dollars worth of material. This single floating mountain holds more wealth than all the treasures in all the kingdoms throughout history. But the true treasure is not the money these rocks might bring. It is what they represent. Freedom from scarcity. An end to digging holes in your beautiful Earth to find the materials that power your world. As you stand beneath the night sky, you are looking up at humanity's future. A future where the metals in your devices don't come from strip mines that scar landscapes. Where the materials that build our cities float freely in space, waiting for us to learn how to reach them gently. The asteroids have been waiting for billions of years. Patient as mountains, silent as snow. They have watched stars be born and die. They have seen planets form and find their places in the cosmic dance. Now they wait for something new. They wait for us. Some asteroids are made mostly of rock, like the mountains you know on Earth. Others are loose piles of rubble, held together by gravity so weak you could jump from one side to the other. But the most precious ones are made of metal. Pure iron and nickel cores that once lived at the heart of small planets, before cosmic collisions broke those worlds apart. These metallic asteroids shine dully in sunlight, like old coins floating in dark water. They are the remnants of worlds that almost were. The hearts of planets that never quite grew large enough to survive the violent early days of the solar system. Tonight, several nations on your Earth are quietly making plans. They are designing robots to visit these floating treasures. They are writing new laws about who can claim what in the endless ocean above your head. They are preparing for a gold rush unlike any in human history. A gold rush that will happen not in dusty canyons, but in the pristine silence of space. The United States has passed laws saying that American companies can keep whatever they mine from asteroids. Luxembourg, a country smaller than most cities, has made itself the center of European asteroid mining law. Japan sends spacecraft to study these rocks up close, learning their secrets. But tonight, as you prepare to rest, the asteroids continue their ancient orbit, unaware of human ambitions. They spin slowly in the cosmic dark, carrying their treasures like patient merchants waiting for customers who are only now learning to travel the roads of space. Some people worry that this new gold rush might lead to conflict. That nations might fight over rocks floating in space, just as they once fought over gold buried in mountains. Others dream of abundance so great that conflict becomes meaningless. When there are more riches than anyone could ever use, what reason is there to fight? The asteroids themselves offer no answers. They simply continue their journey around the sun, as they have for billions of years. But now, for the first time since the solar system formed, intelligent eyes are watching them. Calculating minds are measuring their worth. Human hearts are beginning to dream of what those distant treasures might mean for our future. As your eyelids grow heavy tonight, let your mind drift upward, past the atmosphere, past the pull of Earth's gravity. Float among these silent wanderers. Feel the deep peace of space, where no wind blows and no sound carries. Where ancient mountains drift like sleeping giants through the cosmic dark. But these mountains are not sleeping. They are waiting. And soon, very soon, we will begin to understand exactly what they have been waiting for. Close your eyes and travel backward through time. Not years, not centuries, but billions of years. Back to when there was no earth beneath your feet. No moon to light the darkness. No sun to warm your face. In the beginning, there was only a cloud. This cloud stretched across space, vast beyond imagining. It was made of dust and gas, the remains of ancient stars that had lived and died long before our story began. The cloud drifted in the cosmic dark, cold and patient, waiting for something to wake it from its endless sleep. Then, slowly, gravity began its gentle work. Like invisible hands, gravity reached into the cloud and started to gather. Tiny particles of dust found each other in the darkness. They stuck together, forming larger clumps. These clumps attracted more dust, growing bigger and bigger with each passing million years. At the center of this cosmic dance, the largest clump grew hot and bright. It became our sun, a newborn star that lit up the darkness for the first time. Around it, the leftover material continued to swirl and gather, like leaves caught in a gentle whirlpool. This is where your Earth began its story. In the spinning disk around the young sun, dust grains no bigger than sand stuck together. They formed pebbles. Pebbles became rocks. Rocks crashed into each other and stuck, becoming boulders. Boulders gathered into mountains floating in space. Some of these floating mountains grew large enough to pull themselves into round shapes. Their gravity became strong enough to clear their neighborhoods, sweeping up everything in their path. These became the planets you know today. Earth, Mars, Venus, Jupiter. Each one a successful gathering of cosmic dust. But not everything found its way into planets. Between Mars and Jupiter, something went wrong with the gathering process. Jupiter, the giant of our solar system, was growing so massive that its gravity began to stir up the space around it. Like a large dog running through a field of butterflies, Jupiter's presence scattered the material that might have become another planet. Instead of coming together into one world, the rocks and dust in this region remained separate. They became the asteroid belt, a collection of failed planets. The building blocks that never quite built anything complete. Each asteroid in this belt is a time capsule. A piece of the early solar system, preserved exactly as it was 4.5 billion years ago. While Earth changed and grew, developing oceans and atmosphere, weather and life, the asteroids remained frozen in time. On your Earth, wind and rain have worn down the oldest mountains. Water has carved new valleys and filled them with sediment. Life has covered the surface with forests and coral reefs. The original rocks from Earth's birth lie buried deep beneath layers of newer stone. But the asteroids remember. Their surfaces still show the scars from the violent early days when rocks crashed into each other constantly. They preserved the original chemistry of the solar nebula, the cloud from which everything formed. They are like pages from the universe's first book, written in stone and metal. Some asteroids are made of the same rocky material that formed Earth's outer layers. These are called stony asteroids, and they make up most of the population in the asteroid belt. They are dark and rough, like chunks of volcanic rock floating in space. Others formed from material that sank to the centers of larger bodies during the early days. When those larger bodies were broken apart by collisions, their metallic cores became the iron asteroids we see today. These shiny, heavy rocks are made mostly of iron and nickel, the same metals that flow in Earth's molten core. Then there are the carbonaceous asteroids, the most ancient of all. These dark, carbon-rich rocks formed in the coldest, most distant parts of the early solar system. They contain water, locked in their minerals like memories of cosmic ice. Some scientists think asteroids like these may have brought the first water to Earth, delivering the oceans you know today. As you drift through this ancient story, imagine the solar system as it was then. No blue Earth with white clouds. No red Mars with polar ice caps. Just a collection of growing worlds, gathering themselves from cosmic dust under the light of a young sun. The process was not gentle. Rocks the size of cities crashed into each other at incredible speeds. These collisions created heat so intense that some asteroids melted completely, separating into layers like a cosmic onion. Heavy metals sank to the center while lighter rocks floated to the surface. Over millions of years, the violence slowly calmed. The largest objects had swept up most of the loose material. The planets settled into their current orbits. The asteroid belt found its rhythm, a collection of survivors from the age of formation. But the story of creation was not finished. Even today, asteroids sometimes leave their comfortable orbits in the belt. A gentle gravitational nudge from Jupiter or Mars can send one wandering toward the inner solar system. Some of these wanderers eventually find their way to Earth. When they enter our atmosphere, friction with the air makes them glow bright as stars. You call them shooting stars or meteors. Most burn up completely before reaching the ground. But sometimes, a piece survives the fiery journey and lands as a meteorite. Every meteorite that falls to Earth is a gift from the age of formation. A physical piece of the early solar system, delivered to your doorstep. Scientists study these space rocks like historians examining ancient documents, learning the secrets of how worlds are born. The largest meteorite ever found weighs 60 tons. It sits in Namibia, a chunk of an iron asteroid core that somehow made the journey from the belt to Earth. Children climb on it during school field trips, touching with their small hands the same metal that formed when the sun was young. Tonight, as you prepare for sleep, the asteroids continue their ancient orbit between Mars and Jupiter. They spin slowly in the cosmic dark, carrying their memories of creation. Each one a monument to the time when worlds were young and everything was possible. They have watched Earth change from a ball of molten rock to a world of blue oceans and green forests. They have seen life appear and flourish on the planet they helped to build. And now, they wait patiently as that life begins to look up at the stars and wonder about the treasures hidden in space. But these cosmic time capsules hold more than just memories. Within their ancient hearts lie riches that could transform your world, resources so abundant they might change what it means to be human in a universe full of endless possibilities. Picture yourself floating in the perfect silence of space, drifting toward a mountain that hangs in the cosmic dark. This is not like any mountain you have ever seen on Earth. It has no base anchored to solid ground. No peaks carved by wind and rain. No forests covering its slopes or rivers cutting through its valleys. This mountain simply exists, suspended in nothingness, turning slowly in the gentle light of the distant sun. As you drift closer, you begin to see that this asteroid is not a simple chunk of rock. It has layers, textures, and secrets written across its ancient surface. Every crater, every ridge, every smooth patch tells a story that reaches back to the birth of worlds. The asteroid before you is roughly potato-shaped, tumbling end over end in a rotation that takes several hours to complete. Its surface is a patchwork of light and dark areas, some smooth as river stones, others rough and jagged like broken glass. But what strikes you most is its stillness. No atmosphere surrounds this floating mountain. No wind stirs its dust. No weather erodes its peaks. This asteroid looks exactly as it did a billion years ago, and it will look the same a billion years from now. Not all asteroids are built the same way. The one you are visiting belongs to a family scientists call stony asteroids. These make up about 3/4 of all the space rocks in the asteroid belt. They are composed mainly of silicate minerals, the same materials that form the rocks beneath your feet on Earth. But as you circle this ancient wanderer, you notice something unusual. Parts of its surface gleam with a dull metallic shine. These are veins of metal running through the stone, like silver threads woven into dark cloth. This asteroid formed during the violent early days of the solar system, when heat and pressure mixed rock and metal together in ways that rarely happen on Earth today. Some asteroids are made almost entirely of metal. These are the cores of small planets that never quite grew large enough to survive. During the chaotic period when worlds were forming, these baby planets were smashed apart by cosmic collisions. Their rocky outer layers scattered into space, leaving behind only their metallic hearts. If you could visit one of these iron asteroids, you would find yourself floating beside a mountain made of nearly pure metal. Iron, nickel, and precious metals like platinum and gold flow through these space rocks in concentrations that would make Earth's richest mines look poor by comparison. The strangest asteroids of all are the rubble piles. From a distance, these look like solid mountains floating in space. But as you approach, you realize they are not solid at all. They are collections of loose rocks and boulders, held together by gravity so weak that a gentle push could send pieces floating away. Imagine a pile of stones in a field, but instead of resting on the ground, the entire pile floats in space. The rocks at the center pull on the rocks at the edges, but just barely. The whole structure is so delicate that if you could somehow pick it up and shake it, it would fall apart like a house made of blocks. These rubble pile asteroids formed when larger asteroids collided and shattered. Instead of flying apart completely, the pieces stayed close together, slowly gathering back into a loose collection. They are held together by the weakest force in the universe, yet they have survived for millions of years in the gentle environment of space. Landing on a rubble pile asteroid would be like trying to land on a pile of sand. Your spacecraft would need to approach with incredible care, moving slower than a walking pace. Even then, touching down might disturb the delicate balance that holds the whole structure together. Between the rocks and boulders in these loose asteroids, there are empty spaces. Caves and tunnels thread through the interior like a three-dimensional maze. Some of these spaces might be large enough to park a school bus. Others are no bigger than closets. All of them exist in perfect vacuum, silent and airless chambers that have never known the touch of atmosphere. The surface of any asteroid is a museum of cosmic violence. Every crater marks the spot where another space rock crashed into it at tremendous speed. Some craters are fresh and sharp-edged, created recently in cosmic terms. Others are old and worn, their rims softened by billions of years of micrometeorite impacts. The largest craters tell stories of catastrophic collisions that nearly destroyed the asteroid completely. These giant scars stretch across entire faces of the space mountain, creating cliffs and valleys in the airless landscape. If you could stand at the edge of one of these ancient craters, you would be looking down into a bowl large enough to hold an entire city. But it is not just the craters that make each asteroid unique. Some have strange grooves that run around their surfaces like cosmic scars. Others have ridges that rise up like the spine of a sleeping dragon. A few have smooth areas where space weathering has polished the rock to a dull shine. The colors of asteroids vary from deep charcoal black to reddish brown to metallic gray. The darkest asteroids are made of carbon-rich materials, so black they reflect almost no light at all. These are among the most ancient objects in the solar system, preserving organic compounds from the very beginning of planetary formation. The brightest asteroids are often the youngest, at least in terms of their surfaces. Recent collisions have exposed fresh rock from their interiors, rock that has not yet been darkened by billions of years of space weathering. As you continue to orbit your chosen asteroid, you begin to understand that each of these space mountains is an individual. No two are exactly alike. Each has its own shape, its own composition, its own history written in stone and metal. Some asteroids spin rapidly, completing a full rotation in just a few hours. Others turn so slowly that their day lasts longer than an Earth week. A few tumble chaotically, spinning on multiple axes like cosmic footballs thrown by invisible giants. The gravity on most asteroids is incredibly weak. On a typical space rock a mile across, you would weigh less than a feather. You could literally jump from one side to the other, sailing through the vacuum in a gentle arc that would take several minutes to complete. This weak gravity creates a strange environment where up and down have little meaning. Dust and small rocks can float just above the surface, held in place by the asteroid's feeble pull. Larger boulders sometimes balance on tiny contact points, defying what would seem possible in Earth's strong gravity. Yet within this alien landscape lies incredible wealth. The metals flowing through these floating mountains represent resources beyond earthly measure. Iron for building, nickel for strengthening steel, platinum for electronics, gold for conducting electricity. All of it floating free in the cosmic dark, waiting for humanity to learn the gentle art of space mining. As you prepare to leave this asteroid and continue your journey, you realize that you have been exploring more than just a space rock. You have been examining a treasure chest left over from the creation of worlds, filled with riches that could transform your entire civilization. Imagine holding a ring made of platinum in your hand. Feel its weight, its cool smoothness against your skin. This precious metal is so rare on Earth that all the platinum ever mined by humans could fit inside a single garage. Every piece of it pulled from deep mines, extracted with enormous effort from tons of ordinary rock. Now lift your eyes to the darkness above and consider this: floating in space, there are mountains made almost entirely of platinum. As you drift through the asteroid belt in your imagination, you pass rocks that contain more precious metals than have ever existed in all the treasuries of all the kingdoms in human history. These are not fantasy treasures from fairy tales. They are real, measured by telescopes, confirmed by mathematics, waiting patiently in the cosmic dark. The asteroid called 16 Psyche gleams with metallic light as it tumbles through space between Mars and Jupiter. Scientists believe this single space mountain contains 10 million billion tons of iron and nickel. But mixed within that common metal flows something far more precious. Platinum courses through Psyche's interior like silver veins in marble. Enough platinum to supply Earth's industries for millions of years. Enough to make this single asteroid worth more money than the entire global economy has ever produced. But platinum is just the beginning. Gold, that metal that has driven human dreams and wars for thousands of years, exists in asteroids by the ton. Not scattered in tiny flakes through tons of rock, as it is found on Earth, but concentrated in rich deposits that would make ancient alchemists weep with joy. The rare earth elements that power your phone, your computer, your television, flow through asteroid cores in abundance that defies earthly understanding. These materials, so difficult to find and extract from your planet, drift freely in space, waiting for gentle hands to harvest them. Rhodium, more valuable than gold, exists in asteroid hearts in quantities that could crash Earth's precious metal market simply by arriving home. Palladium, essential for electronics and clean energy, flows through space rocks like water through underground rivers. But why do asteroids hold such incredible wealth while Earth seems so poor in comparison? The answer lies in how planets form. When your Earth was young and molten, gravity pulled the heaviest materials toward the center. Iron, nickel, platinum, and gold sank deep into the planet's core, leaving the lighter rocks to form the crust where you live. Most of Earth's precious metals lie thousands of miles beneath your feet, mixed into the molten iron core that creates the planet's magnetic field. They are forever out of reach, locked away in temperatures hot enough to melt any metal humans have ever created. But asteroids tell a different story. Some asteroids are the exposed cores of small planets that never quite grew large enough to survive. During the violent early days of the solar system, these baby worlds were shattered by cosmic collisions. Their rocky outer layers were blown away, leaving behind only their metallic hearts. These iron asteroids are essentially pieces of planetary core, floating free in space. All the heavy metals that would normally be buried deep inside a world are right there on the surface, accessible to gentle mining techniques. Other asteroids formed in regions of space where heavy metals never had a chance to sink to the center. They remained mixed throughout the rock, creating concentrations of precious materials that dwarf anything found on Earth's surface. A single metallic asteroid the size of a football stadium could contain more platinum than humans have ever mined. An asteroid the size of a city block might hold enough rare earth elements to power Earth's electronics industry for decades. The economic implications are staggering. If just one medium-sized metallic asteroid were brought to Earth, it could supply enough precious metals to make these materials as common as aluminum. The scarcity that makes platinum and gold so valuable would vanish overnight. But the true revolution would not be in the price of jewelry or investment metals. It would be in technology itself. Right now, many advanced technologies remain expensive because they require rare materials. Fuel cells that could power clean cars need platinum. Solar panels work better with silver. Advanced electronics require rare earth elements that are difficult and environmentally damaging to mine. When these materials become abundant through asteroid mining, technologies that are currently too expensive for widespread use could become as common as smartphones. Cars powered by hydrogen fuel cells could fill every driveway. Solar panels could cover every roof, not because governments mandate it, but because the materials become cheap enough to make it profitable. The environmental benefits could be even more profound than the economic ones. Most of Earth's mining operations scar the landscape, pollute water supplies, and displace communities. Mining asteroids would leave your planet's surface untouched while providing far greater quantities of raw materials. Imagine a world where no new mines need to be dug. Where the metals in your devices come not from strip-mined mountains but from rocks floating freely in the vacuum of space. Where the rare earth elements in your phone were harvested by robots in the cosmic dark, leaving Earth's wilderness pristine and undisturbed. But accessing these space treasures requires solving challenges that no mining company has ever faced. Space is not like Earth, where miners can set up camps, bring in heavy equipment, and work in familiar conditions. Asteroid mining must happen in perfect vacuum, where no air exists to carry sound or moderate temperature. Equipment must function in conditions that swing from blazing heat when facing the sun to bitter cold in shadow. There is no gravity to hold things in place, no atmosphere to protect against radiation. Yet these challenges also create opportunities. Without gravity to fight, massive chunks of valuable metal could be moved with surprisingly little energy. Without atmosphere to cause weather or erosion, mining equipment could operate for decades without maintenance. The metals themselves would be incredibly pure. Earth-based mining must deal with metals that have been mixed and contaminated by billions of years of geological processes. Asteroid metals often exist in their original form, uncontaminated by chemical reactions that require expensive purification processes. Some visionaries imagine asteroid metals being processed directly in space, never brought to Earth at all. Giant space-based factories could turn raw asteroid metal into finished products, from solar panels to spacecraft to orbital habitats. Earth would become the customer, not the factory, receiving manufactured goods from space-based industries. The timeline for this transformation remains uncertain. Current technology can barely reach asteroids, let alone mine them profitably. But private companies and government agencies are making steady progress, developing the tools and techniques needed to unlock space wealth. Several asteroids have been visited by robotic explorers, mapping their surfaces and analyzing their composition. These scouting missions are like the first explorations of Gold Country, identifying the richest targets for future mining operations. The first asteroid mining missions will likely focus not on precious metals but on water. Water found in asteroids can be split into hydrogen and oxygen, the same chemicals that power rocket engines. Space-based fuel depots fed by asteroid water could make travel through the solar system as routine as crossing an ocean. But as the infrastructure grows and techniques improve, the focus will inevitably shift to the incredible wealth locked in metallic asteroids. The platinum rivers that flow through space rocks will eventually find their way to Earth, or perhaps more importantly, will fuel the growth of industries that never need to touch Earth at all. Tonight, as you settle into sleep, those rivers of platinum continue their ancient orbit around the sun, patient as mountains, wealthy beyond measure, waiting for humanity to develop the gentle technology needed to tap their abundance. Forget everything you know about mining on Earth. Forget the thunderous blasting of mountainsides. Forget the grinding of massive machines against stone. Forget the dust and noise and violence of tearing precious metals from unwilling rock. In space, mining becomes something entirely different. Something gentle. Something that looks more like gardening than destruction. Picture a small spacecraft approaching an asteroid with the patience of a butterfly landing on a flower. There is no rush here, no deadline imposed by weather or the need to shelter workers from harsh conditions. In the perfect vacuum of space, time moves differently. Slowly. Thoughtfully. The mining spacecraft does not crash into the asteroid like a wrecking ball. Instead, it drifts closer with movements so subtle they are barely visible. Tiny thrusters fire in controlled bursts, each one no stronger than a gentle breath. The spacecraft settles onto the asteroid's surface as softly as snow falling on still water. But even calling it landing is not quite right. In the weak gravity of an asteroid, the spacecraft does not land so much as it simply stops moving. Gentle anchors extend like spider legs, finding purchase in the rocky surface. The entire process takes hours, maybe days. There is no hurry in the cosmic dark. Once attached, the real work begins. But this work looks nothing like the mining you know on Earth. Instead of drilling deep holes and filling them with explosives, the mining robot uses heat. Solar panels spread like metallic flowers, gathering sunlight and concentrating it into laser beams so focused they can melt rock without disturbing the material around it. The laser traces delicate patterns across the asteroid's surface, like an artist drawing with light. Where the beam touches, rock vaporizes into gas that drifts away into space. Slowly, carefully, the robot cuts channels and trenches, exposing the metal veins hidden beneath layers of stone. Some asteroids surrender their treasures through magnetism. Powerful electromagnets, no larger than dinner plates, create invisible fields that reach into the rock. Iron and nickel respond to this call, separating from surrounding minerals and floating gently toward the collection chambers. It is like watching invisible hands sort through a box of mixed materials, picking out the valuable pieces with perfect precision. The waste rock drifts away, unwanted but unharmed. The precious metals gather in neat piles, ready for processing. Other mining techniques use chemistry instead of force. The robot sprays carefully designed chemicals onto the asteroid's surface. These chemicals dissolve only specific metals, leaving everything else untouched. The dissolved platinum or gold flows like invisible streams into collection tanks. This process, called leaching, happens so gently that it barely disturbs a grain of dust on the asteroid's surface. The robot is not conquering the space rock. It is having a conversation with it, asking politely for its treasures. For carbonaceous asteroids rich in water and organic compounds, the mining process resembles cooking more than traditional extraction. Gentle heat warms sections of the asteroid until water trapped in the rock becomes steam. The steam is captured and condensed back into liquid water, pure and clean. This water becomes the most valuable resource in space. Not for drinking, though it could serve that purpose, but for fuel. Water can be split into hydrogen and oxygen using electricity from solar panels. These two gases, when combined and ignited, provide the thrust that powers rocket engines. An asteroid mining operation becomes a fuel station floating in space. Spacecraft traveling through the solar system can stop to refill their tanks, just as cars stop at gas stations on long highway journeys. This turns space from an empty desert into a network of oases, each one making the next destination reachable. The beauty of space mining lies in its precision. On Earth, mining operations must move tons of worthless rock to extract ounces of valuable metal. The environmental cost is enormous. Mountains are leveled, valleys are filled with waste, and rivers run cloudy with mining runoff. But in space, there is no environment to protect. No atmosphere to pollute. No wildlife to displace. The waste rock from asteroid mining simply drifts away into the cosmic void, where it joins the natural collection of space debris that has been floating between worlds since the solar system formed. The energy costs of space mining also work differently than on Earth. Here, you must fight gravity every time you want to move something heavy. Lifting a ton of ore from the bottom of a mine to the surface requires tremendous energy. In space, once something starts moving, it keeps moving without any additional energy. A chunk of platinum asteroid could be gently nudged toward Earth and would coast for months or years, requiring only small course corrections along the way. The processing of space-mined materials happens in zero gravity, creating possibilities that do not exist on Earth. Metals can be purified using techniques that depend on the absence of gravity. Alloys can be created that would be impossible to make in Earth's heavy environment. Some visionaries imagine entire factories floating in space, turning raw asteroid materials into finished products. Solar panels more efficient than any made on Earth. Electronics using ultra-pure metals that have never been contaminated by atmospheric exposure. Spacecraft built from materials that never had to escape a planetary gravity well. The timeline for these operations stretches across decades, not months or years. A single asteroid mining mission might take 10 years from launch to the return of processed materials to Earth. But the payoff from that single mission could supply Earth's industries for decades. The robots that do this work must be extraordinarily reliable. They cannot be repaired by human technicians if something breaks. They must function perfectly for years at a time, in conditions ranging from the blazing heat of direct sunlight to the bitter cold of space shadow. These mining robots are being designed like living creatures, with redundant systems and the ability to adapt to unexpected conditions. If one tool fails, another takes its place. If the asteroid proves different than expected, the robot adjusts its techniques. Some of the most advanced designs include robots that can build copies of themselves using materials found on asteroids. These self-replicating miners would create entire colonies of mining equipment, spreading from asteroid to asteroid like mechanical seeds carried by cosmic winds. The first asteroid mining operations will likely target near-Earth asteroids, space rocks that pass relatively close to our planet. These are easier to reach than the main asteroid belt, requiring less fuel and shorter travel times. But even close in space terms means distances that dwarf anything on Earth. The nearest asteroid mining targets are millions of miles away, further than humans have ever traveled. Getting there requires patience, precision, and technology that is just now being developed. Several companies and space agencies are testing the techniques needed for asteroid mining on Earth-based laboratories and in space-based experiments. They are learning how metals behave in zero gravity, how to control chemical processes in vacuum, and how to build robots sturdy enough for decade-long missions. As you drift toward sleep tonight, somewhere in laboratories and cleanrooms around your world, engineers are designing the gentle tools that will unlock space wealth. They work with the same careful attention to detail that the mining robots themselves will use, knowing that precision and patience will prove more valuable than brute force in the cosmic environment above your head. But before these robotic gardeners can begin their delicate harvest, nations must answer a question that grows more urgent each day: who has the right to claim these floating treasures, and what happens when multiple countries reach for the same cosmic prize? In quiet government buildings around your world, officials sit in meetings that would have seemed like science fiction just a decade ago. They are not discussing borders between countries or trade agreements for earthly goods. They are writing laws about rocks that orbit the sun millions of miles away. These are not dreamers or science fiction writers. They are practical politicians and business leaders, economists and space engineers. And they are all looking up at the same dark sky, seeing the same infinite opportunity floating in the cosmic void. The United States was among the first to act. In 2015, Congress passed a law with a simple but revolutionary idea: if an American company travels to space and mines an asteroid, that company can keep whatever it finds. The law does not claim that America owns the asteroid itself. It simply says that Americans can own the materials they extract from it. This distinction matters more than it might seem. It is like the difference between owning a mountain and owning the gold you dig out of that mountain. The mountain remains wild and free, but the gold becomes yours through the work of extraction. Other nations watched this American law with great interest. Some saw opportunity. Others saw the beginning of a new kind of competition that could reshape the balance of power on Earth. Luxembourg, a country so small you could drive across it in an hour, decided to make itself the center of European asteroid mining. This tiny nation, nestled between France and Germany, passed laws even more welcoming to space mining companies than America had created. Luxembourg began attracting space mining startups like flowers attract bees. Companies from around the world opened offices in this small European country, drawn by laws that promised clear ownership rights and minimal bureaucratic obstacles. The country's leaders understood something important. Luxembourg had built its economy on being a helpful middleman for other people's money. Now they wanted to be the helpful middleman for other people's space rocks. Japan approached the challenge differently. Instead of just passing laws, Japan launched spacecraft to visit asteroids and study them up close. The Japanese Space Agency, JAXA, sent probes to asteroids named Itokawa and Ryugu, landing on their surfaces and even returning small samples to Earth. These missions were not about immediate mining. They were about learning. How do you navigate to an asteroid? How do you land on something with almost no gravity? How do you collect samples without damaging your equipment? Each mission answered these questions and raised new ones. The samples that returned to Earth were tiny, just a few grams of space dust and rock fragments. But they represented something much larger. They proved that humans could travel to asteroids, touch them, and bring pieces home safely. China began its own quiet asteroid exploration program, launching missions to study near-Earth asteroids and developing the technology needed for future mining operations. Chinese officials speak carefully about their intentions, but their actions suggest serious interest in space resources. Russia, drawing on decades of space experience from the Soviet era, started partnerships with private companies to develop asteroid mining technology. The Russians understand rockets and space navigation as well as anyone, knowledge that could prove valuable in the emerging space mining industry. Even smaller nations found ways to participate. The United Arab Emirates, a country that built its wealth on earthly oil, began investing heavily in space technology. UAE leaders speak of preparing for a future when energy comes not from underground petroleum but from space-based solar power and asteroid-derived materials. Private companies, not just governments, began the serious work of developing asteroid mining technology. Companies with names like Planetary Resources and Deep Space Industries attracted investors who believed that space mining would become the next great industry. These companies faced a challenge unlike any in human history. They needed to develop technology that had never been tested, for an industry that did not yet exist, to mine materials from destinations that were farther away than humans had ever traveled. Yet investors poured money into these ventures, understanding that the potential rewards were as vast as space itself. A single successful asteroid mining mission could return more wealth than most companies earn in their entire existence. The early focus was not on precious metals but on water. Water found in asteroids could be converted into rocket fuel, making space travel cheaper and more practical. This was the key that could unlock everything else, a way to refuel spacecraft without having to launch everything from Earth's expensive gravity well. Several companies began designing spacecraft specifically for asteroid water mining. These were not the sleek, elegant ships of science fiction movies. They were practical, industrial-looking machines designed to spend years traveling through space and then patiently extract resources from floating rocks. The technology needed for asteroid mining pushed the boundaries of what was possible. Solar panels that could operate efficiently at the distance of the asteroid belt. Communication systems that could send signals across hundreds of millions of miles. Robotic systems that could function perfectly for years without any possibility of repair. International cooperation began to emerge alongside competition. No single nation had all the technology needed for successful asteroid mining. American companies provided spacecraft. European firms contributed precision robotics. Japanese engineers shared navigation expertise. Russian partners offered launch capabilities. But cooperation came mixed with tension. If asteroid mining proved as profitable as projections suggested, early success could shift global economic power in ways that had not been seen since the discovery of oil or the Industrial Revolution. Nations that succeeded in asteroid mining could gain access to materials that were scarce or expensive for everyone else. Countries with advanced space mining industries might become the new economic superpowers, while nations that remained earthbound could find themselves at a serious disadvantage. Some officials worried about the emergence of what they called space mining colonialism. Would wealthy nations with advanced space technology drain resources from asteroids while poorer countries remain dependent on limited earthly materials? Others saw asteroid mining as the great equalizer. If space resources proved as abundant as scientists predicted, even small nations could gain access to materials that had previously been available only to the richest countries. The timeline for these developments remained uncertain. Optimistic projections suggested that commercial asteroid mining could begin within a decade or two. More conservative estimates pushed the timeline out to mid-century or beyond. But the preparation was happening now. Laws were being written. Technologies were being developed. Partnerships were being formed. The infrastructure for a space-based resource economy was taking shape in laboratories, boardrooms, and government offices around your world. International space law, written decades ago when asteroid mining was pure fantasy, struggled to keep up with these new realities. The 1967 Outer Space Treaty declared that no nation could own celestial bodies, but it said nothing about owning materials extracted from those bodies. This legal gap created both opportunity and uncertainty. Companies could proceed with asteroid mining plans, but they could not be completely sure that other nations would recognize their claims. The lack of clear international agreements left room for future disputes. As you prepare for sleep tonight, negotiators and engineers in different time zones continue their work on humanity's next great adventure. They are laying the groundwork for an industry that could transform not just economics, but the very relationship between Earth and the rest of the solar system. But even as nations race to develop the technology and legal frameworks for asteroid mining, a more fundamental question remains unanswered. What happens when the infinite abundance of space meets the ancient human habit of turning cooperation into competition? Imagine trying to write laws for a world that does not yet exist. Picture legal scholars sitting around polished tables, crafting rules for situations no human has ever faced. This is the challenge facing lawmakers as they grapple with the ownership of floating mountains in the cosmic dark. The question seems simple on its surface. If you travel to an asteroid and mine platinum from its core, who owns that platinum? But like most questions about space, the answer becomes complex the moment you begin to examine it closely. In 1967, when humans had barely touched the moon, representatives from around the world gathered to write the Outer Space Treaty. They created a document filled with noble ideals and gentle language. Space, they declared, was the province of all mankind. No nation could claim ownership of celestial bodies. Exploration should be peaceful, conducted for the benefit of everyone on Earth. The treaty was written in an age when asteroid mining existed only in the imaginations of science fiction writers. Its authors could not have envisioned private companies launching robots to harvest platinum from space rocks. They were thinking about flags planted on the moon, not about the economics of cosmic wealth. Today, that treaty feels both too restrictive and not restrictive enough. It forbids nations from claiming asteroids as territory, but says nothing about whether companies can claim the materials they extract from those asteroids. This gap in the law has created space for both opportunity and uncertainty. Legal experts spend their days puzzling over questions that would have seemed absurd to previous generations. If an American company mines gold from an asteroid, does that gold belong to America? To the company? To all of humanity? What happens if two companies from different countries arrive at the same asteroid at the same time? Some lawyers argue that asteroid mining violates the spirit of the Outer Space Treaty. If space belongs to everyone, they say, then its resources should benefit everyone equally. Private companies should not be allowed to claim exclusive rights to cosmic wealth. Others counter that the treaty forbids claiming asteroids themselves, but not claiming materials extracted from them. They point to similar principles in Earth-based law. No one owns the ocean, but fishing companies can own the fish they catch. No one owns Antarctica, but researchers can own the ice samples they collect. The distinction between owning an asteroid and owning materials from that asteroid may seem trivial, but it carries enormous practical importance. If companies cannot claim exclusive rights to their extracted materials, there would be little incentive to invest in the expensive technology needed for space mining. International law moves slowly, like a glacier advancing across a landscape. While lawyers debate and diplomats negotiate, companies and nations make plans based on their own interpretations of existing rules. This creates a situation where different countries may have different ideas about what is legal in space. The United States has declared that American companies can keep whatever they mine from asteroids. Luxembourg has made similar promises to European firms. But Russia and China have been more cautious about making such declarations. This patchwork of national laws creates uncertainty about how disputes might be resolved. What happens if a Japanese company and an American company both claim mining rights to the same asteroid? There is no space police force to resolve such disputes. No international court with clear jurisdiction over cosmic property rights. The legal framework that governs most human activities simply does not extend beyond Earth's atmosphere. Some visionaries propose creating new international institutions specifically for space governance. A cosmic equivalent of maritime law, with recognized courts and enforcement mechanisms. Others suggest that existing international bodies like the United Nations should expand their authority to cover space activities. But creating effective space law faces challenges that earthly lawmakers never encounter. Enforcement becomes nearly impossible when the disputed territory is millions of miles away. How do you serve legal papers to a mining operation orbiting the Sun between Mars and Jupiter? The vast distances and long timelines of space operations also complicate traditional legal concepts. If two companies launch missions to the same asteroid, but one arrives 5 years before the other, does timing determine ownership? What if the first company abandons its mining operation after a few years? Environmental law becomes particularly complex in space. On Earth, we have regulations about air and water pollution because we all share the same atmosphere and water supplies. But each asteroid exists in its own bubble of vacuum. Mining operations there cannot pollute in any traditional sense. Yet some legal scholars worry about space pollution of a different kind. What happens if asteroid mining operations leave debris that interferes with spacecraft navigation? Who is responsible for cleaning up abandoned mining equipment that might pose hazards to future missions? The question of salvage rights adds another layer of complexity. If a mining spacecraft breaks down on an asteroid, can competitors claim its equipment? Maritime law has clear rules about salvaging ships in distress, but those rules were written for oceans, not for the vacuum between worlds. Some of the most interesting legal questions involve the concept of jurisdiction. If a crime is committed on a mining station attached to an asteroid, which country's laws apply? The nationality of the spacecraft? The nationality of the perpetrator? The location of the parent company's headquarters? These may seem like abstract legal puzzles, but they have practical implications for anyone planning to work in the space mining industry. Miners, engineers, and executives need to know which laws govern their activities and which courts might hear disputes about their work. The timeline for resolving these legal uncertainties remains unclear. International law typically develops slowly, through decades of negotiation and gradual consensus building. But the pace of technological development in space mining may force faster decisions. Some companies have decided not to wait for perfect legal clarity. They are proceeding with asteroid mining plans under existing laws, accepting the legal risks in exchange for potential first-mover advantages. This approach could work well if their interpretations prove correct, but could lead to expensive disputes if courts disagree. As you settle into sleep tonight, legal scholars in different time zones continue their work on humanity's most exotic legal challenges. They are trying to extend human law into the infinite cosmos, creating rules for situations that exist nowhere except in the vast darkness above your head. But even as lawyers craft elegant solutions to questions about cosmic ownership, a more fundamental challenge looms. What happens to human society when scarcity itself becomes a thing of the past, and abundance flows down from the stars like gentle rain? Close your eyes and imagine walking into a store where everything costs the same as a loaf of bread. The diamond necklaces, the gold watches, the platinum wedding rings. All of them priced like everyday groceries because the materials they are made from have become as common as sand on a beach. This is the world that asteroid mining promises to create. A world where scarcity transforms into abundance so complete that it changes the very meaning of wealth. For thousands of years, human civilization has been built on the foundation of scarcity. Gold is valuable because it is rare. Diamonds cost fortunes because they are difficult to find and extract. Platinum powers the most advanced technologies but remains expensive because Earth holds so little of it within easy reach. But floating in space, patient as sleeping giants, asteroids contain these precious materials in quantities that could satisfy human needs for millions of years. A single metallic asteroid might hold more platinum than humans have ever mined throughout all of history. When that abundance reaches Earth, something remarkable will happen. The economic laws that have governed human society since the beginning of trade will suddenly reverse. Instead of rationing scarce resources, we will face the challenge of managing infinite plenty. Consider what this means for the simplest objects in your daily life. Your smartphone contains tiny amounts of rare earth elements that currently cost hundreds of dollars per pound to extract from Earth's crust. When asteroid mining makes these materials abundant, phones could become so cheap to manufacture that they might be given away like promotional items. The catalytic converters in cars require platinum to clean exhaust fumes. Today, these devices cost thousands of dollars, making them frequent targets for thieves. In a world of asteroid-derived platinum abundance, catalytic converters might cost no more than plastic bumpers. Solar panels work most efficiently when made with silver, but silver's high cost limits how much can be used in their construction. When space mining makes silver abundant, solar panels could be built with optimal amounts of precious metals, making clean energy far more efficient and affordable. But abundance brings challenges that human societies have never had to face. What happens to the mining towns built around extracting scarce resources from Earth? What becomes of the communities whose entire economies depend on the rarity of materials that space makes common? In the mountains of Chile, families have worked copper mines for generations. Their children grow up expecting to follow the same paths, extracting valuable metal from deep underground shafts. When asteroid mining makes copper abundant, these communities will need to find new purposes, new ways to contribute to a world that no longer needs their traditional skills. The jewelry industry faces a similar transformation. Diamond mines in Africa employ hundreds of thousands of people whose livelihoods depend on the rarity of these crystalline gems. If asteroid mining discovers caches of diamonds in space rocks, an entire industry built on scarcity could collapse overnight. Yet abundance also creates opportunities that scarcity makes impossible. Advanced technologies that remain too expensive for widespread use could become available to everyone. Medical devices requiring rare metals could be distributed globally. Clean energy systems could be built without worrying about the cost of scarce materials. The environmental implications are even more profound than the economic ones. Most of Earth's mining operations leave lasting scars on the landscape. Mountains are leveled to reach metal deposits. Rivers are diverted or polluted by mining runoff. Entire ecosystems are disrupted by the search for valuable materials. When mining moves to space, Earth's landscapes could begin to heal. Strip mines could be allowed to become forests again. Polluted rivers could run clean. The environmental cost of human civilization could finally begin to decrease instead of constantly growing larger. But the transition from scarcity to abundance will not happen overnight. Asteroid mining will begin with the most valuable materials, slowly working down the list of precious resources. The first materials to become abundant will likely be the rarest and most expensive ones. This creates a paradoxical situation. The people who currently benefit most from scarcity, the owners of diamond mines, precious metal deposits, and rare earth extraction operations, will be the first to see their wealth diminish. Meanwhile, people who have been priced out of using advanced technologies will suddenly find them affordable. The social implications ripple outward like waves from a stone dropped in still water. If advanced materials become cheap enough for everyone to use, the gap between rich and poor countries could narrow dramatically. Nations that lack natural resources could finally compete on equal footing with countries blessed by geological fortune. Educational systems will need to adapt to a world where abundance replaces scarcity as the primary economic reality. Children will grow up in a world where the fundamental assumptions about value and rarity no longer apply. They will need new frameworks for understanding how societies organize themselves around plenty instead of shortage. The psychology of abundance presents challenges that few humans have ever experienced. Throughout history, people have been motivated by the need to secure scarce resources for themselves and their families. When everything becomes abundant, what drives human ambition and innovation? Some economists worry that extreme abundance could lead to economic collapse. If precious metals become worthless through abundance, entire financial systems built on their value could crumble. Stock markets, currency systems, and international trade relationships all depend on scarcity-based assumptions about value. Others see abundance as humanity's liberation from artificial constraints. They argue that scarcity has always been an enemy of human potential. When materials become abundant, human creativity and ingenuity can finally focus on problems more important than fighting over limited resources. The timeline for this transformation remains uncertain. Even optimistic projections suggest that asteroid mining will take decades to reach the scale needed to make precious materials truly abundant. The transition will likely be gradual, giving societies time to adapt to new realities. But the early signs of change are already visible. Companies developing asteroid mining technology attract investors who believe that space abundance will reshape civilization. Governments write laws preparing for industries that do not yet exist. Engineers design robots for mining operations that may not begin for decades. In research laboratories around your world, scientists study how materials behave in zero gravity, preparing for manufacturing processes that will take place entirely in space. These space-based industries could produce goods that never touch Earth's surface, using materials extracted from asteroids to build products for use throughout the solar system. The cultural impact of abundance extends beyond economics and technology. Throughout human history, stories and myths have celebrated the heroes who find rare treasures. What kinds of stories will humans tell when treasure becomes commonplace? How will literature and art adapt to a world where scarcity is no longer the driving force behind human drama? Religious and philosophical traditions that emphasize the spiritual value of material simplicity may find new relevance in a world of material abundance. When physical needs are easily satisfied, human attention may naturally turn toward questions of meaning, purpose, and spiritual fulfillment. The asteroid miners of the future may be remembered not as people who made rare materials common, but as the generation that freed humanity from the ancient tyranny of scarcity. They will be the ones who opened the door to a future where human potential is no longer constrained by the accidental distribution of valuable materials on a single planet. As you drift toward sleep, somewhere above your head, those future treasures continue their patient orbit around the sun. They carry within their metallic hearts the power to transform not just human wealth, but human nature itself. But before that transformation can begin, humanity must first answer a more immediate question: what happens when infinite wealth meets finite human wisdom, and how much can a species accustomed to competition learn to embrace the economics of cosmic plenty? Picture a world where numbers lose their familiar meaning. Where calculations that once seemed impossible become routine. Where economists stare at spreadsheets filled with figures so large that they strain the very concept of mathematics itself. This is the strange mathematics of asteroid mining economics, where a single space rock might contain wealth measured not in millions or billions, but in quintillions of dollars. The asteroid 16 Psyche, floating patiently between Mars and Jupiter, contains an estimated $10,000 quadrillion worth of materials. This number is so large it becomes almost meaningless. It represents more wealth than every economy on Earth combined, multiplied by millions. Yet here lies the central paradox of cosmic economics. The very abundance that makes asteroid mining so attractive could destroy the value of what it seeks to harvest. Imagine a farmer who discovers a field that produces infinite wheat. At first, this seems like the greatest fortune imaginable. But when infinite wheat enters the market, the price of wheat drops to nearly nothing. the farmer's infinite harvest becomes infinitely worthless. This same principle applies to asteroid mining, but on a scale that dwarfs any earthly analogy. When platinum flows from space in unlimited quantities, platinum prices must inevitably fall. When gold arrives by the ton instead of by the ounce, gold loses its status as a precious metal. The mathematics of supply and demand, taught in every economics classroom, becomes twisted into strange new shapes when applied to cosmic abundance. Supply curves that once rose steadily now stretch toward infinity. Demand curves struggle to adapt to resources that never run out. Traditional economic models break down when faced with truly unlimited resources. These models assume that scarcity drives value, that limited supply creates demand. But asteroids contain materials in quantities so vast that scarcity becomes a concept from another era. Some economists propose that asteroid mining will create its own new economic laws. Instead of competing for scarce resources, companies will compete to be the first to bring abundant resources to market. Speed becomes more valuable than efficiency. Innovation matters more than conservation. The early asteroid mining companies may indeed earn enormous profits, capturing high prices before abundance drives those prices down. Like gold prospectors who arrived first at newly discovered fields, the space mining pioneers could become wealthy beyond imagination. But their wealth would be temporary. As more companies launch asteroid mining operations, as more space rocks are harvested, the flood of precious materials would eventually drive prices toward zero. The very success of the industry would undermine its own profitability. This creates a race against time for space mining investors. They must recover their initial investments and earn profits before abundance makes their products worthless. The window of opportunity may be measured in decades, not centuries. Yet even as precious metals lose their value through abundance, new forms of value begin to emerge. When materials become cheap, the creativity and knowledge needed to use those materials wisely become more valuable. Design becomes more important than raw resources. Ideas matter more than ingredients. The companies that thrive in an era of asteroid abundance may not be the ones that extract materials most efficiently. Instead, success may belong to those who find the most creative ways to use unlimited resources. Art and innovation could become the new forms of wealth. Consider how this transformation has already happened with other resources in human history. Aluminum was once more precious than gold, so rare and difficult to extract that Napoleon served his most honored guests with aluminum plates while lesser guests received gold ones. Today, aluminum is so common we throw it away without thought. The development of efficient aluminum production techniques transformed this metal from ultimate luxury to everyday commodity. Yet the industries that emerged around abundant aluminum, aviation, electronics, packaging, created far more wealth than the aluminum mining industry ever had. Space mining may follow a similar pattern. The true value may not lie in the extracted materials themselves, but in the technologies and industries that cheap space materials make possible. Space elevators built with abundant carbon nanotubes from asteroids. Solar power satellites constructed with unlimited space metals. Space habitats housing millions of people, built with materials that would have been impossibly expensive to launch from Earth. The financial markets struggle to price companies whose primary assets are measured in quantities that have never existed before. How do you calculate the value of a company that owns mining rights to rocks containing more wealth than human civilization has ever created? Stock analysts create new mathematical models, trying to predict how markets will behave when abundance replaces scarcity as the fundamental economic driver. Their computers run simulations based on assumptions that have never been tested by reality. Some investors bet that asteroid mining companies will become the most valuable enterprises in human history. Others argue that the very abundance these companies seek to create will make their business models obsolete before they can achieve profitability. The currency implications alone could reshape global finance. If asteroid mining floods Earth with precious metals, currencies backed by gold could become worthless overnight. Nations would need to find new foundations for their monetary systems, perhaps based on energy or information rather than physical materials. International trade relationships, built over centuries around the exchange of scarce resources, would need complete reconstruction. Countries that became wealthy by controlling access to rare materials would lose their economic advantages. Nations rich in knowledge and innovation might become the new economic superpowers. Insurance companies face the challenge of providing coverage for operations involving risks and rewards that have never existed before. How do you calculate premiums for missions to asteroids worth more than entire countries? What happens if a mining operation succeeds too well and crashes the market for its own products? The environmental economics become particularly interesting when Earth's resources no longer need to be exploited. If asteroid materials satisfy all human needs, natural resources could become valuable for their own sake rather than for human use. Forests valued for being forests, not lumber. Mountains appreciated for their beauty, not their mineral deposits. Yet the transition period between scarcity and abundance could create economic chaos. Traditional resource-based economies would collapse before new abundance-based systems could develop. Millions of people employed in Earth-based mining, drilling, and extraction industries would need to find new purposes. The social safety nets required to manage this transition would need to be stronger and more flexible than anything human societies have ever created. Entire regions dependent on resource extraction would need economic transformation programs on scales never attempted before. But perhaps most intriguingly, asteroid abundance could force humanity to redefine the very concept of wealth. In a world where material needs are easily satisfied, what becomes valuable? Time becomes more precious when things are cheap. Experiences matter more when objects are common. Relationships gain importance when material competition decreases. The psychological economics of abundance remain largely unexplored territory. How do humans find motivation and meaning in a world where material scarcity no longer drives behavior? What new forms of competition and cooperation emerge when the old rules no longer apply? As you drift toward sleep tonight, somewhere in corporate boardrooms and university economics departments, brilliant minds are trying to model these unprecedented scenarios. They work with equations that stretch mathematics to its limits, attempting to understand wealth so vast it might transform the very meaning of value itself. But even as economists struggle with infinite abundance, a more immediate question looms: will humanity approach these cosmic riches as partners working toward shared prosperity, or will the same competitive instincts that have driven earthly resource conflicts follow us into the stars? In the quiet darkness of space, floating mountains of metal wait patiently for humanity's arrival. They have no armies to defend them, no borders to mark their territory, no flags planted on their surfaces to claim ownership. They simply exist, turning slowly in the cosmic dark, unaware of the human dreams and ambitions they inspire. But down on Earth, in boardrooms and government offices, people study maps of asteroid orbits with the same intensity that conquistadors once examined charts of unknown continents. The question that haunts these modern explorers is ancient and familiar: will the search for cosmic treasure bring out humanity's best impulses or its worst? History offers sobering lessons about what happens when humans discover vast new sources of wealth. The California gold rush of 1849 began with individual prospectors panning hopefully in mountain streams. It quickly evolved into industrial mining operations, claim disputes, and violence between competing groups. The silver rushes of Nevada, the diamond discoveries of South Africa, the oil booms of Texas and Alaska all followed similar patterns. Initial cooperation gave way to competition. Competition bred conflict. Conflict often erupted into violence as the stakes grew higher and the easy wealth became harder to find. Each resource rush brought out both the noble and the ignoble aspects of human nature. Prospectors helped each other survive in harsh conditions, sharing food and shelter when times were difficult. But they also fought over claims, cheated partners, and sometimes killed competitors for access to the richest deposits. The asteroid belt contains wealth that dwarfs all of these earthly treasures combined. If history repeats itself, the scale of potential conflict could be proportionally enormous. Nations with spacefaring capabilities might become the new colonial powers, claiming asteroids the way European countries once divided up continents. Yet space mining also offers humanity a chance to break free from these destructive historical patterns. The asteroids contain so much wealth that traditional concepts of scarcity may not apply. When there is enough platinum for everyone, why fight over individual deposits? The unique environment of space could encourage cooperation in ways that earthly resource extraction never has. No single nation has the complete set of technologies needed for successful asteroid mining. American rocket technology might need European robotics, Japanese navigation systems, and Russian launch capabilities. International partnerships in space have already proven more successful than many earthly collaborations. The International Space Station represents the longest-running peaceful cooperation between former enemies in human history. American astronauts and Russian cosmonauts work side by side, their national differences insignificant compared to the shared challenge of surviving in space. This cooperative spirit could extend naturally to asteroid mining. When the technical challenges are enormous and the potential rewards are unlimited, collaboration makes more sense than competition. Companies from different nations might find it more profitable to share costs and expertise than to duplicate each other's efforts. The legal framework for space mining also encourages peaceful approaches. The Outer Space Treaty declares that space exploration should benefit all mankind, not just the nations wealthy enough to reach the asteroids first. While this treaty has gaps and ambiguities, its underlying philosophy promotes sharing over hoarding. Some visionaries propose creating international asteroid mining consortiums, similar to the organizations that manage Antarctica or coordinate deep-sea research. These collaborations could ensure that space wealth benefits humanity as a whole rather than creating new forms of inequality between spacefaring and earthbound nations. But cooperation requires trust, and trust can be fragile when vast wealth is at stake. Nations that cooperate in exploring asteroids might find their relationships strained when those asteroids prove to contain riches beyond imagination. Historical allies could become competitors if the potential profits are large enough. The timeline of space mining also creates opportunities for both cooperation and conflict to evolve. Early missions will likely focus on near-Earth asteroids that are relatively easy to reach. These targets are limited in number, creating natural competition between companies and nations that want to claim the best sites. As space technology improves and costs decrease, mining operations could spread throughout the asteroid belt, where targets are virtually unlimited. This expansion could reduce competitive pressures by ensuring that everyone has access to profitable mining sites. The environmental advantages of space mining might also encourage cooperative approaches. Earth-based mining operations often create conflicts between environmental protection and economic development. Communities fight over whether to allow mining in pristine wilderness areas. Nations struggle to balance resource extraction with ecological preservation. Space mining faces no such conflicts. Asteroids have no ecosystems to protect, no indigenous populations to displace, no scenic landscapes to preserve. Mining them causes no environmental damage that could spark protests or regulatory battles. This removes one of the major sources of conflict in earthly resource extraction. Yet new forms of conflict could emerge in the space environment. Nations might fight over orbital routes that provide efficient access to valuable asteroids. Companies could dispute the boundaries between mining claims on irregularly shaped space rocks. Accidents or equipment failures could create debris that threatens everyone's operations. The military implications of space mining capabilities also raise concerns about peaceful use. The same rockets that can reach asteroids could potentially be weaponized. The same technologies that can manipulate asteroid orbits for mining purposes could theoretically be used to redirect space rocks toward Earth. Some defense experts worry about the emergence of asteroid powers that could threaten Earth-based nations with space-launched weapons. Others dismiss these concerns as science fiction, pointing out that asteroid mining companies have no incentive to destroy their customer base on Earth. The economic scale of space mining might actually reduce international tensions by making traditional resource conflicts obsolete. When platinum, gold, and rare earth elements become abundant through space mining, nations will have less reason to fight over earthly deposits of these materials. Resource-based conflicts in Africa, disputes over Arctic oil reserves, and tensions over rare earth monopolies could all become irrelevant if space mining provides unlimited alternatives. Traditional geopolitical advantages based on resource control could shift to new advantages based on space technology and access. The speed of technological development in space mining will likely influence whether cooperation or competition dominates. If progress remains slow and expensive, nations and companies might have time to develop cooperative frameworks before the stakes become enormous. But if breakthrough technologies suddenly make asteroid mining cheap and easy, a space-based gold rush could develop faster than international cooperation can manage. Rapid technological change has often disrupted careful diplomatic arrangements in the past. Cultural factors may also influence how humanity approaches space mining. Societies with strong traditions of individual competition might approach asteroids differently than cultures that emphasize collective cooperation. These cultural differences could become more pronounced when the potential rewards reach unprecedented scales. The generation currently designing space mining systems will likely determine whether humanity becomes cosmic conquistadors or peaceful pioneers. Their decisions about technology development, international cooperation, and legal frameworks will shape how space resources are accessed and distributed. Educational systems around the world are beginning to prepare students for careers in space industries, emphasizing both technical skills and international cooperation. These future space miners, engineers, and managers may approach cosmic resources with different values than previous generations of earthly prospectors. As you prepare for sleep tonight, somewhere in the darkness above, those patient asteroids continue their ancient orbits, unaware that they may become either humanity's greatest treasure or its greatest test. The choice between cooperation and competition, between sharing and hoarding, between peace and conflict in space, remains unwritten in the stars. But that choice will not remain unmade forever, and when it is finally decided, the consequences will ripple not just through space, but through every aspect of human life on the small blue world that these cosmic treasures could transform. Look around your bedroom as you prepare for sleep. The smartphone charging on your nightstand. The LED lights casting a gentle glow. The laptop resting on your desk. Each of these familiar objects connects you to an invisible network of rare materials extracted from deep within Earth's crust. Your smartphone alone contains tiny amounts of 17 different rare earth elements, each one carefully mined from distant locations around the world. The screen relies on indium. The battery needs lithium and cobalt. The circuits require gold and silver. The speakers use neodymium magnets. But tomorrow's world, shaped by asteroid mining, could free these everyday objects from their dependence on earthly scarcity. The ripple effects of cosmic abundance will flow through your daily life like gentle waves, transforming the familiar in ways you might not immediately notice. Consider what happens when the rare earth elements in your devices become as common as sand. Electronics manufacturers will no longer need to choose between performance and cost. They can build phones with the optimal amount of each material, creating devices that work better, last longer, and cost less to produce. Your next smartphone might have a screen so clear and bright it seems to glow within a light. Its battery could last for days without charging because unlimited lithium allows for better battery designs. The processing speed could increase dramatically when manufacturers can use optimal amounts of rare metals in computer chips. But the changes extend far beyond better gadgets. The solar panels that might one day cover your roof will work more efficiently when built with unlimited amounts of silver and rare earth elements. Instead of compromising on materials due to cost, engineers can design panels that capture every possible ray of sunlight. Electric cars, currently expensive partly because of their rare metal requirements, could become as affordable as regular automobiles when asteroid mining makes those materials abundant. The catalysts in their fuel cells can be made with optimal amounts of platinum. Their motors can use powerful rare earth magnets without concern for cost. The environmental ripple effects might prove even more transformative than the technological ones. Right now, your lifestyle carries an invisible environmental cost measured in mining operations scattered around the globe. Every electronic device you own required mountains to be moved, valleys to be filled, and landscapes to be scarred. When mining moves to space, Earth begins to heal. The copper mines of Chile could close and return to wilderness. The rare earth mining operations in China, which currently pollute vast areas to supply the world's electronics, could shut down as space-derived materials take their place. The cobalt mines of the Democratic Republic of Congo, where children sometimes work in dangerous conditions to extract materials for batteries, could become obsolete when asteroid mining provides unlimited alternatives. The human cost of your technological lifestyle could finally begin to decrease. Forests that were cleared for mining operations could regrow. Rivers that run red with mining runoff could flow clean again. Wildlife displaced by extraction operations could reclaim their ancient territories. Your planet's landscape could begin to look more like it did before industrial mining began. The medical technologies that keep you healthy could become far more advanced and widely available. Many cutting-edge medical devices require rare metals that are currently too expensive for widespread use. Asteroid abundance could make these life-saving technologies as common as basic medical supplies. Advanced cancer treatments that use targeted nanoparticles containing rare metals could become available to everyone. Diagnostic equipment requiring precious metals for optimal sensitivity could be installed in every clinic. Implantable devices that currently cost fortunes due to their rare metal components could become routine medical tools. The city where you live will transform in subtle but profound ways. Streetlights could become more efficient and longer lasting when built with unlimited rare earth elements. The infrastructure hidden beneath your streets, the electrical grids, communication networks, and transportation systems, could all be upgraded using materials that were previously too expensive for optimal design. Architecture itself might change when structural metals become abundant through space mining. Buildings could be designed with materials chosen for beauty and performance rather than cost. Bridges could last longer and require less maintenance when built with optimal metal alloys. Even the food you eat could be affected by asteroid mining abundance. Modern agriculture depends on fertilizers containing elements that are currently mined from limited earthly deposits. When space mining makes these materials abundant, food production could become more efficient and less environmentally damaging. The packaging around your food could change too. Right now, manufacturers balance protection and cost when choosing materials for food containers. Unlimited access to optimal metals could create packaging that keeps food fresher for longer while being completely recyclable. The economic ripples will touch your financial life in ways both obvious and subtle. If precious metals become abundant, your investments might need rebalancing. Gold and silver, traditionally considered safe investments, could lose their value as space mining floods the market with these materials. But new investment opportunities will emerge. Companies involved in space mining, space-based manufacturing, and the industries that develop around abundant materials could become the growth sectors of tomorrow's economy. The jobs of the future might involve managing abundance rather than rationing scarcity. Your education system will need to adapt to a world where the fundamental assumptions about value and scarcity no longer apply. Children will learn economics in a world where material abundance allows human creativity to focus on problems more interesting than fighting over limited resources. The entertainment you enjoy could become more spectacular when the materials needed for advanced displays, sound systems, and virtual reality equipment become cheap enough for everyone to access. The line between imagination and reality could blur as technology becomes limited only by human creativity rather than material costs. Scientific research could accelerate dramatically when advanced instruments become affordable for every laboratory. Experiments that are currently impossible due to the cost of rare materials could become routine. Medical research, climate science, and space exploration could all advance more rapidly when equipped with unlimited access to optimal materials. The transportation networks that connect your world could be revolutionized. Hyperloop systems requiring strong, lightweight materials could become economically viable. Magnetic levitation trains using powerful rare earth magnets could connect cities with transportation systems that are faster, quieter, and more efficient than anything currently possible. Even your leisure activities might be touched by space abundance. Sports equipment could be made with optimal materials regardless of cost, improving performance for everyone from weekend athletes to Olympic competitors. Musical instruments could use the best possible materials, making beautiful sounds accessible to musicians at every level. The air you breathe could become cleaner as abundant materials enable better pollution control systems. Catalytic converters in cars could use optimal amounts of platinum, removing more pollutants from exhaust. Industrial facilities could afford better filtration systems when the materials are no longer prohibitively expensive. The timeline for these changes will likely stretch across decades rather than years. The transformation will be gradual, with abundance slowly replacing scarcity in one industry after another. You might not notice the changes from day to day, but looking back across years, the cumulative effect could be revolutionary. Some changes will be immediately visible. Others will be hidden in the improved performance of familiar objects. Your phone might work better without you knowing that it contains materials that were once more valuable than gold. Your car might run cleaner without you realizing that its catalytic converter uses platinum that came from space. The psychological effects of living in abundance rather than scarcity remain largely unexplored. How does human behavior change when material limitations no longer constrain creativity and innovation? How does society function when the ancient struggle for scarce resources becomes a memory from a different era? As you settle into sleep, your room filled with objects that connect you to mining operations around the world, imagine waking in a future where those same objects connect you instead to the gentle harvest of floating mountains in space. But that future world, abundant with cosmic treasures, will need inhabitants who can appreciate not just material wealth, but the deeper transformations that unlimited resources might bring to human consciousness itself. Picture a child who has never known scarcity. She grows up in a world where platinum is as common as aluminum, where rare earth elements flow as freely as sand on a beach. Her toys are made with materials that were once more precious than gold. Her school supplies contain elements that your generation fought wars to control. This child lives in tomorrow's world, shaped by the gentle harvest of floating mountains in space. To her, asteroid mining is not science fiction or economic theory. It is simply how the world works, as normal as fishing from the ocean or growing food in fields. She learns about the early 21st century in history class, studying a time when people worried about running out of materials, when countries competed for access to rare metals, when mining required digging holes in beautiful landscapes. To her, these stories seem as strange and distant as medieval tales of dragons seem to you. Her textbooks describe the Great Scarcity period when humans believed that valuable materials were limited and must be rationed carefully. She reads about wars fought over oil, about conflicts arising from mineral deposits, about environmental destruction caused by the desperate search for rare earth elements. These historical accounts puzzle her young mind. Why didn't people just go to space for materials? Why did they damage their own planet when floating mountains of metal drifted patiently above their heads? The answers her teachers provide seem to describe a different species entirely. She grows up expecting abundance as naturally as you expect gravity. When her phone breaks, she doesn't worry about the cost of replacement because the materials inside are virtually free. When she wants to build something for a school project, she chooses materials based on their properties, not their price. Her generation approaches problems differently than yours. When faced with a challenge, they don't ask what can we afford. They ask what works best. Scarcity-based thinking is as foreign to them as abundance-based thinking is revolutionary to you. The careers available to her reflect this transformed world. She might become a space resource coordinator, managing the gentle flow of materials from asteroids to Earth. Or a materials optimization specialist, finding the best uses for abundant resources. Perhaps an abundance counselor, helping older generations adapt to a world without material limitations. Her education emphasizes creativity and innovation over conservation and rationing. Art classes use precious metals like clay because the materials are abundant enough to experiment with freely. Science labs have unlimited access to rare elements for student experiments. Engineering projects are constrained only by imagination, not by the cost of components. She learns to think in ways that your generation struggles to understand. Problems that seem impossible to you due to material constraints appear solvable to her. Technologies that you consider too expensive to implement seem obviously beneficial to her mind, shaped by abundance. The games she plays as a child prepare her for a world of unlimited material possibilities. Instead of learning to share scarce resources, she learns to manage abundance wisely. Instead of competing for limited supplies, she collaborates on projects that would have been impossible in the age of scarcity. Her relationship with the natural world differs fundamentally from yours. She grows up knowing that Earth's landscapes are preserved not because materials are too valuable to extract, but because extraction is no longer necessary. The forests and mountains are beautiful for their own sake, not threatened by the human need for the materials they contain. She visits national parks that are healing from centuries of mining damage. The rivers run cleaner because industrial processes use abundant space-derived materials instead of Earth-extracted resources. The air is purer because optimal amounts of rare metals make pollution control systems incredibly effective. Her generation faces different ethical questions than yours. Instead of debating whether to allow mining in pristine areas, they discuss how to use unlimited materials responsibly. Instead of fighting over who controls scarce resources, they consider how best to manage cosmic abundance. She learns about space not as a distant frontier, but as humanity's extended neighborhood. The asteroid belt is mapped and catalogued like a familiar territory. Mining operations throughout the solar system supply materials as routinely as farms supply food. Space-based industries manufacture goods that never touch Earth's surface. Her perspective on interplanetary relationships reflects this expanded view. Mars is not another world but another province. Jupiter's moons are not alien territories but familiar places where her civilization harvests materials and energy. The entire solar system is humanity's home, not just the single planet where her species evolved. Yet she also inherits challenges that your generation could never have imagined. What does it mean to live a meaningful life when material wants can be easily satisfied? How does a society function when traditional motivations based on scarcity no longer apply? How do humans find purpose in a world where ancient struggles have been resolved? Her textbooks describe the philosophical transformations that accompanied material abundance. The great thinkers of the late 21st century who helped humanity adapt to unlimited resources. The new forms of art and culture that emerged when creativity was no longer constrained by the cost of materials. She grows up during humanity's second great transformation, comparable to the agricultural revolution that changed humans from hunters and gatherers into farmers. Just as that ancient change created civilization as you know it, the abundance revolution creates a civilization that would seem impossible to your generation. The stories her parents tell her about the old days seem like myths from another world. They describe a time when people hoarded materials, when rare metals were locked in vaults like treasure, when entire industries existed just to manage scarcity. These tales fascinate her the way stories of knights and castles fascinate children today. Her dreams are different from yours. Where you might dream of finding buried treasure or striking it rich, she dreams of discovering new ways to use abundant materials, of creating beautiful things that were impossible in the age of scarcity, of solving problems that your generation couldn't even attempt. As she grows older, she begins to understand that her world of abundance was not inevitable. She learns about the engineers and visionaries who developed asteroid mining technology, the diplomats who prevented space conflicts, the economists who managed the transition from scarcity to plenty. She develops a kind of historical empathy for your generation, understanding that you lived in a world where difficult choices were necessary because resources were limited. She appreciates the sacrifices and compromises that her ancestors made, even as she enjoys freedoms that your generation could barely imagine. Her children will grow up even further removed from the age of scarcity. To them, her stories about the early days of asteroid mining will seem like ancient history. They will inhabit a solar system where human civilization spans multiple worlds, all supplied by the gentle harvest of cosmic materials. Tonight, as you prepare for sleep in your world of material limitations and careful resource management, that future child exists only as potential. She waits to be born into the world that your generation's choices will create. Whether she grows up in abundance or continues to struggle with scarcity depends on decisions being made now, in boardrooms and laboratories, in government offices and international conferences, by people who are designing humanity's relationship with the infinite treasures floating patiently in the cosmic dark above your head.